exploring the intersection of resilient technology, organizations, and people. REdeploy.
Hi everyone, I'm Nora. I'm super excited to be here today. I'm really excited for this conference. I've been looking forward to it for months. Paul and Mary have done such an excellent job today and have been so accommodating. Chaos engineering is the discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. It's not about inserting chaos. It's about the chaos that's already inherent in the system and being able to engineer around that. It helps the user explore unknown unknowns of their system and instill more confidence. I'm Nora Jones. I work on chaos engineering at Netflix, and today I'm going to share some of my experiences building the chaos tools at my company and working with the people that use them. So I'm going to split my talk into two sections. I'm going to have an in-theory portion and an in-practice portion. So you'll see a in-practice talk to note the intermission between the two sections. So the first half of my talk is going to focus on some of the theory and human factors components, and the second half is going to focus on the technical specifics. So I want to start with, why do we even do chaos engineering? What's the point of it? Why do we do failure injection? Why do we do stress testing? Why unit testing? Why any of these things? For chaos engineering, is it to find vulnerabilities? This might seem like an obvious answer, right? We want to find vulnerabilities. We want to expose them. But it doesn't really end there. That's not quite the answer. Jonathan Van Ness is one of my favorite characters. He will appear again later. So, you know, it might be easy to say, wow, chaos is such a success at my company. We found 205 vulnerabilities last quarter. What does that even mean, though, right? Like, you know, I feel like if you wanted to go into a code base and look for a bunch of vulnerabilities, you could probably find 205 vulnerabilities. But the important thing to note here is why were these vulnerabilities important? What did they mean? How did they drive the company forward? So at first glance, an easy answer might be to find stuff. We want to find vulnerabilities. But from the Error of Counting Errors by Robert Wares, he says that error counts are measures of ignorance rather than risk. You don't know much about safety by just counting errors or by just counting vulnerabilities. The goal of chaos engineering isn't to simply find vulnerabilities. The goal is to push forward on this journey towards resilience. And what do I mean when I say resilience? Resilience is the ability of a system to adjust so that it can sustain normal functioning in the face of changes and disturbances. And when I say system here, I'm not simply talking about the technical specifics. I'm also talking in terms of the humans that operate the technical parts of the system. Because the humans, their attitudes, and the trade-offs that they're making under pressure, these are all contributing factors into how the system works. Now, doing chaos engineering isn't the means to an end of achieving resilience. That's not what I'm here to talk to you about today. It is a slice of that pie, though. It does help us in some regards, and I'm going to show you how it could help you. So when you find a vulnerability through chaos tooling or through what you're using, you want to find out what happened. So you want to find out what happened culturally. How does the team balance conflicting priorities? How do they trade things off? Whether these are explicit or not. Sometimes they may know these things. Sometimes you might have to observe them yourself. You have to find out what happened technically. How difficult were changes to be made? Were shortcuts taken? Was this intentionally not done? Sometimes when we find vulnerabilities, you know, we find out the team is like, yeah, we know about that, right? But they didn't know how important it was. And so it's important to capture why there was a discrepancy there, or maybe inform your chaos tools better. Hey, this is something that might not be worth fixing right now. And attitude-wise. So there are changes in behaviors from externally driven factors, and they are effective. What externally driven factors were successful in driving a change? So sometimes they might be actually the chaos tools. You know, it might take a tool or something to change the process, to change the culture, but this is a trial and error thing. It's not going to be a one-size-fits-all within every team in your company because, as you all are probably aware, even within small companies, each team has micro-cultures. They all have their own cultures. It's not just one big encompassing culture in a company. Different things are going to work for different teams, and it's important to capture that as someone that's on an internal tools team or a chaos engineering team. So an anti-goal with chaos engineering is to be a rule enforcer. So Mark Maron from Glow has a nice quote: "Everybody's going to hate you." Well, I don't want everybody to hate me. That's not my job here. My job is not to be a rule enforcer. My job is not to look for all the ways that services aren't following best practices. My job is to give context into why the vulnerabilities the chaos tools are finding may be bad and how we could go about addressing them. Simply requiring and reminding people to be safer and more careful and follow best practices doesn't actually end up helping. It ends up actually being a bit manipulative and often quite infantilizing. It assumes that someone isn't the expert in a given situation. So you want to give them as much context as possible. A person developing chaos tools and using them effectively, you are a service owner's partner. You're not their rule enforcer. You're not there to bring the hammer down on them. Another anti-goal is to not cause more problems for people, not to cause chaos, not to break things. And I'll get into how we do that effectively at Netflix later on in the presentation. Now, and I want to bring up an important point. It's not done to cause problems. It is done to reveal the problems. So how do you form a culture around chaos engineering, a culture where failure is embraced because it's inevitable? I want to share a quote from Gene Rochlin. He's part of a project at Berkeley called the High Reliability Organization Project, and they spend time studying groups that seem to do the impossible, operate highly complex and hazardous technological systems essentially without making mistakes. And so he says here, safety is not defined as the absence of error or the control of a risk. The complete absence or suppression of errors or accidents is not possible. That's not the goal of chaos engineering. Vicky said that earlier too. We can't get to zero accidents, right? We can't get to zero errors. The goal is to improve our ability to react and handle these issues when we are inevitably faced with them, and to be better prepared and to be able to control the blast radius effectively. So, one of the goals is to improve our ability to react to errors in a way that ensures that the customer doesn't have a bad experience, that the operator of the service doesn't have a bad experience, and that we can learn from said error. I think we often focus on number one, right? We really want to make sure that the business stays intact, and that is very important. But we also want to keep in mind, the operators, right? People get burned out very easily. We want them to be confident when dealing with issues. And if we do have an issue, we want to be able to learn from it and capture those learnings from it effectively. And here's Jonathan again. He's very excited. When you find a vulnerability, you might get excited. You might say, wow, my tool found something. Like it did what it's supposed to do. We might think, oh my gosh, we saved Netflix from a big issue here by finding this vulnerability. And we should be happy because we found a very interesting failure mode that could only be found under this specific set of circumstances. However, the important thing to note here is that the story doesn't stop there. Safety is more than just the management or avoidance of this risk or error. So I think it's really easy to, if you do find a vulnerability, and if you see it in the code right away, wow, I know what went wrong. It could just be a single line change. Like maybe I could even submit a pull request to this team and dial that knob. And that may be easy to do, and the team may even thank you for that. But I want to emphasize that it's important to not just dial that knob, to actually dive into why that knob needs to be dialed to begin with, because the set of circumstances that cause that to happen, may still be there and are probably worth addressing. So another goal is to capture the learnings from vulnerabilities. Operators and engineers must continue to learn. So how do you capture these learnings? Communication is very important here. As a chaos engineer, capturing the learnings from a vulnerability it's important to do the following and share this with the team. It's important to share, what did you exactly experiment on? Why was that experiment derived? How did you derive that experiment? What was the analysis of your results? And what are your recommendations? So my colleague Haley Tucker actually does a phenomenal job at giving teams this context when she finds a vulnerability. And I think all these things are very important here because they address questions like concerns teams might have over, is this really worth addressing right now? How did they even come up with this? And why did they experiment on this particular thing? That helps give them context too, and it helps develop and strengthen that partnership. When sharing a vulnerability with the team that owns the service, it's important to put yourselves in the shoes of the service owner. And I saw this quote recently, and it was actually about a ship, and it says, "It's impossible for anyone who hasn't worked on such a ship to understand the complexity, stress, and hazards of its operations." And I think we could substitute ship for service there. It's impossible for anyone that hasn't worked on such a service to understand the complexity, stress, and hazards of its operations. You know, service owners are the experts in this situation, but we are providing them more context in order for them to make the best decisions within their roles. The engineers that work on these services are making explicit trade-offs every day in order to make their services work. There may be a reason that they didn't fix the thing that you found, or they may not even know it was there to begin with. Regardless, there is a story to be captured there. If they didn't know it, there's definitely a reason behind that as well. So, and although that exact failure may be prevented from happening again, the contributing factors to the failure mode might still be unexplored. So I want to go to in practice for a little bit. I'm going to spend some time exploring exactly how chaos engineering is implemented at Netflix and some of the things that we have found and explored along the way. So some of our main focuses when we do chaos engineering are safety and monitoring. We want to make sure that, you know, we have good safety mechanisms in place for not only our customers, but for our coworkers and operators as well, so that we're not unintentionally paging people. And also monitoring. We want to see exactly what is going on during a chaos experiment and be able to halt it if needed. So we do this through a tool called CHAP, which is our chaos automation platform. So CHAP can catch vulnerabilities before they become full-blown outages. And it allows you to inject failure or latency into your services in production to validate your assumptions about these services before they become full-blown outages. So I'm going to take you through at a high level how it works. So here's a hypothetical set of microservice dependencies. There's a proxy that sends requests to service A, which then fans out to service B, C, and D. Service D talks to Cassandra, and service B talks to a cache. So I'm going to condense this graph a little bit. It's going to get quite busy in a second. So if we want to see if service B is resilient to the failure of a cache, the user goes to the CHAP interface and selects this service as the service that will observe the failures, and the cache as the service that fails. So CHAP will go ahead and clone service B into two replicas. We have a service B control and a service B experimental. So these are much smaller in size than actual service B. We're not taking all the traffic from service B. We're taking a very, very small amount, and we're calculating that percentage based on a few things. We're calculating it based on the size of the cluster itself, the current SPS, which is our stream starts per second, our key business metric. But the user can adjust it if needed. We do have a maximum threshold, though, so that we're not taking too much of the main traffic and just taking enough so that we can actually get a signal into what's going on. Not too low that we don't get any signal, but not too high where we're actually harming a lot of customers and, you know, expanding our blast radius. So it will then instruct our failure injection testing service, or FIT, to tag these requests that match our criteria. So it does this by adding information to the header of this request. It creates two sets of tags. One set will have instructions to both fail and be routed to the experiment cluster, and the other will just have instructions to be routed to the control cluster. So when the RPC client in service A sees instructions that it needs to route the request, it will send them to the control or the experiment cluster. So once failure injection testing in the RPC layer of the experiment cluster sees that the request has been tagged for failure, it will return a failed response. The experiment cluster will see that as a failed response from the cache and will execute the code to handle this failure. From the point of view of service A, everything looks normal. Since all the requests to the cache fail for the experiment cluster, we can see exactly what would happen if an entire cluster fails without actually failing everything. And so I mentioned here that monitoring is super important while we do things. And so these are actual graphs that the user can see while they're executing a CHAP experiment, or they can go look at them afterwards. The blue line represents the metrics for the control. The red line represents the metrics for the experiment. So you can compare them as time goes on. So if we look at the first graph on the left, it shows the number of calls that were successful. So you can see from the control that all the calls were successful, and there were 0 successes from the experiment, which is to be expected. And then we look at the middle column. So this service shows fallback successes. So you can see there were a lot of failures that were successfully handled in the experiment and returned, which is great. But the last column shows us that for some calls in the experiment, we were not able to render a fallback, which is problematic, right? So here we can actually tell that we were not able to do things the way that we expected them to be done. And we were able to expose that through doing this chaos experiment in a controlled manner. So it's super important to strongly consider customer impact when you're approaching your chaos experiments and proceed with caution where appropriate. We have a canned automated canary analysis configuration for SPS, which is our key business metric, our stream starts per second, aka can a user actually watch the movie or video the movie or TV show that they want to watch. And so if the SPS deviates too far from the in between the control and the experiment in either direction, if it's too high or too low, CHAP will automatically short the experiment, and it detects this in a matter of seconds. So the customer will not have a bad experience. We will shut the experiment off, and they will get routed to a normal service. And then this gives the operator time to actually sit and debug what's going on without being under the fire of a pager, without tweet storms coming down saying, I can't watch Netflix right now, my life is over. Like, they don't have to deal with all that. They can be a lot less stressed. So there are a few other CHAP protections as well that are very important. We limit the total % of traffic impacted in each region, right? So if we see multiple experiments going on in US West 2, and someone wants to run a new experiment in US West 2, we will make sure that not too much traffic is taken from US West 2, and we will just queue that experiment until the other runs are finished completing. We only run during business hours. We do not want to page our colleagues at 3 in the morning if something goes wrong. So we make sure that they are at their desks and ready to handle the situation if they need to. If a test does fail, if a chaos experiment does fail and we did find something weird, it will not actually run again until someone, either a chaos engineer or a service owner, comes in and manually resolves that experiment, says, hey, I understand this was an issue. I'm OK with running an experiment on it again. We do have some where we found an issue, and we're not going to fix that issue, right? We are now noted that, oh, this is a critical service, or this should not be experimented on. And then we also have the ability to apply custom fast properties, which allows users to test different configuration settings before deploying them and rolling them out completely. So if you want to test a new timeout, if you want to test retries and see how it responds under this safe and controlled environment, you can do that without actually deploying it all the way to production. CHAP has found a lot of vulnerabilities, and we've dug into each of them. Here are some examples of my favorite ones. This user says, we ran a CHAP experiment which verifies that the service's fallback path works, which is crucial for our availability. And it successfully caught an issue in the fallback path, and it was resolved before it resulted in any availability incident. So this particular customer, they hadn't seen their fallback execute in a long time. Things had been running pretty successfully. And so how do you know that it still works? So they were able to verify, they were able to see that it actually was not working as expected. And when inevitably that would need to kick off again, they knew that it was going to work now that they actually got the chance to fix it. Another one of my favorite ones, and this was a little bit of a different approach, we ran an experiment to reproduce a sign-up flow fallback issue that happened with certain deploys and intermittently at night. So there was some weird pattern between this failure mode. We were able to reproduce this by injecting 500 milliseconds of latency. And by doing the experiment, we were able to find the details in that log file that was uploaded to the big data portal. And this helped build context into why the sign-up fallback experience was actually only being served during certain pushes. So this specific user actually used CHAP not to see if they were resilient, but they tried to reproduce something that was happening and learn more about it under a controlled condition that was safe. So how do users and chaos engineers at Netflix go about setting up CHAP experiments? In order to do this, we had a few success stories, and so we wanted to get a bunch more chaos experiments running. And so in order to do that, we met with a few critical service owners, we met with some non-critical service owners, and we had to sit down and look at all the possible injection points we could use for a chaos experiment. So there are a lot of injection points that CHAP can support. We have Cassandra, GeoService, EV Cache, Hystrix, RPC service, RPC client, Amazon S3, and SQS. And then these are all the injection points. You also have to decide, do you want to inject failure into these injection points? Do you want to inject latency into these injection points? Or you can even do latency causing failure experiments. So it's a lot of different scenarios that you can come up with. You can even combine injection points into a scenario as well. And then on top of that, users had to decide which automated canary analysis configurations they wanted to include in their experiment. When a user decides that configuration they might want to add, and then subsequently analyze those at the end of the experiment to determine if there's an issue. We had some canned ACAs to aid setup. We have a CHAP SPS automated canary analysis, and this is added by default to every CHAP experiment to look at our key business metric, our stream starts per second. We have CHAP system ACA, which looks at memory, CPU, garbage collection, and load average. We also have CHAP request, which shows RPS successes and failure metrics, and then CHAP injections, which is actually more for us to see if are we actually injecting failure properly? Is this chaos experiment doing what we expect it to do? If it's not, we will shut that experiment down early. So as you can probably tell, experiment creation can be rather time-consuming. And we're not going to get all the benefit that we want to get out of it by having it be time-consuming, by sitting in a bunch of meetings. The user had to create an experiment based on n-factorial types of inputs. The user potentially added ACA configs. The user analyzed the ACA configs at the end of the experiment. And there was very little insight into prioritizing what was important. How do we know what to experiment on right now? It's very hard to come up with, and hold all this information in your head into what makes a good chaos experiment. We were adding cognitive burden to the teams, and we weren't getting as much value out of CHAP as we could have. There were a lot of long meetings. And no one likes those. And plus, on top of the complexity of experiment creation, this is what the actual traffic flow through services at Netflix looks like. It is a lot of cognitive overload for a person or a set of people to be able to keep solely in their heads. We had this goal with CHAP. We wanted to chaos all the things, and we wanted to run all the time during business hours. So let's go back to CHAP. We knew we could use CHAP to help with this. So we decided to zoom in a bit on the services that we were analyzing. When we sat with these teams, we looked up their configurations. We looked up how many times they were being called to see how important they were. We looked at whether or not they had fallbacks, and it took a really long time to gather all that. where we said, maybe we can do this through chat. Maybe we can gather this information through chat. So we zoomed in, we got cute, we gave Chap a monocle, which is crucial optics on the services that can be used to both create and prioritize important experiments. So we thought back to all of our injection points and what we needed to fuel those experiments. So we gathered data on timeouts, we gathered data on retries, percentage of requests certain dependencies were involved in, requests per second. We looked at latency over a 2-week period, and that reoccurs every 2 weeks. And we looked at Hystrix commands, fallbacks and timeouts, and whether or not they were aligned with all the other things going on in the dependency. Hystrix, I realize some people might not be familiar with that. It provides circuit breakers for us when the system reaches a certain threshold. The circuit will open up and actually stop sending requests to the downstream circuit. Once it recovers, it will close, and it also provides things like bulkhead patterns and fallbacks, i.e. when the service fails, do X instead, maybe serve a less personal response. To illustrate that, I'll take a look at this specific Netflix screen. So this might be something that you see when you sign into Netflix regularly. We'll take a look at this continue watching row. So we call our rows at Netflix LOLAMOs, or lists of maps. And so this is a continue watching row. We're looking at our row history. Say we have a fallback for this. Say that we're not able to load this history correctly. Now, that shouldn't result in you not being able to use Netflix. That shouldn't result in you not being able to press play. It should result in something like a fallback. Maybe the fallback is we don't show you anything. Maybe the fallback is we show you popular, recently watched titles. It shouldn't look like this, because then people get sad. I get sad. So luckily, using resiliency testing in the form of KX experiments, we're able to catch errors like these. So that's one thing that we wanted to collect, insights that we wanted to collect when we were creating experiments, as to whether people had fallbacks correctly included in Hystrix commands. So we collected a bunch of this info, and we realized, well, if it was very hard for us to get, it's probably really hard for service owners to access this as well. And so we decided to display all this information for people to actually use and consume. And I realize this might be a little hard to see. I apologize for that. So this is what Monocle looks like. Essentially, you have the ability to see all the dependencies associated with their cluster. And so each row represents a dependency. These are RPC services. You can see the clients associated with them. You can see their timeouts. You can see how many retries they have, how much percent of requests they're actually taking up, what their maximum RPS is, and then associated Hystrix commands. And so we use this information to score a certain type of experiment's criticality and actually feed it into an algorithm that determines prioritization. So using the algorithm to score each experiment based on things like its criticality, its results of the last run, et cetera, et cetera. And so if you actually click into each of the clients, you can see their latency over the past couple weeks relative to their timeout. So here's an interesting example where the timeout is set at 500, and here's the average latency going down way at the bottom. So what happens when that actually spikes up to the timeout? Maybe we don't know because that doesn't happen very often. So it's important to say, it's important to look at this and say, is this the appropriate timeout to set? Do we know what happens when it gets up there? Should we lower the timeout and possibly introduce retries instead? So there's a lot of questions that this visualization and that having this info elicits to the user. And would it be a good experience if it actually got up to the timeout? Would the user even want to wait that long? So this is an exercise I actually go through with some people at Netflix. It's called Let's Find the Vulnerability. And so this is what they see when they log into Monocle. I don't know if you guys can see that very well, but I will do my best to explain it to you. So we have a service called sample service, and it has two NIWS clients associated with it. We have sample rest client.get and sample rest client. So one of these has has an issue associated with it that doesn't make it safe to fail. So this one's okay. Sample rest client.get has a timeout of 200 with one retry associated with it. This is fine because it's a total of 400 milliseconds, which is well within this Hystrix timeout limit. However, sample rest client has timeouts of 100 and 600 with one retry, which is well over the 500 millisecond limit for Hystrix. And so in this case, the retry might not have a chance to complete given the surrounding Hystrix wrapper timeout, which means that Hystrix will abandon the request before NIWS or the RPC client has had a chance to actually return. So why did this happen, right? We actually saw a lot of these when we put them all in the same place, and it was a little scary at first. Like, have we been seeing this all along and not even realize it? And fixing it's very easy. We can maybe tweak some knobs, right? Submit a few pull requests, change a few configuration files. But who's to say that's not going to happen again, right? When they spin up a new service, who's to say that that's going to be informed correctly now that this is all in the same place? In this case, the timeouts for these settings lived in a few different configuration files in different repositories, and it made it difficult to draw conclusions with associations in the logic. With Monocle, we actually are trying to make it easier for users to understand if they're operating services that have anti-patterns like this and flagging them as such. As we all know, changes can sometimes, be very dangerous, but yet there's something that we have to deal with quite frequently. So we used all this info for automatic experiment creation. So remember before we had all these different types of inputs and things to think about. We worked to automate the creation of these and the running of these so that users don't have to. So we automated them. Users can still create them on their own if they want, but we automated in the creation and prioritization of latency, failure, and latency-causing failure for the RPC and Hystrix injection points. We had ACA configs added by default, SPS, system metrics, and request statistics, and experiments are automatically run during the day as well, based on a prioritization algorithm. So how did we prioritize the experiments that we created here? So this is some of the information that we would see in each dependency. And so users can kind of deduce how we're creating experiments and how we're prioritizing them based on what they're seeing in their Monocle. So this is at a high level, and each of these components are weighted, but we use the RPF stats range bucket and the number of retries a dependency has, as well as the number of Hystrix commands associated with it. We also look at things like number of commands without a fallback and curated impacts. If the dependency is known to have an impact, or if the commands don't have fallbacks, we know it's not safe to fail. And we actually weigh these negatively. And so they'll still get a criticality score. It'll just be a negative criticality score. And if it's below 0, they will never get run until these things get fixed, if they decide it's worth fixing. So what else do we use Monocle for? So users can actually click into their dependencies and add known impacts to it. So if I knew that this particular dependency had a sign-up impact or add an SPS impact, I could click into it and add it and know that it would be marked as unsafe to fail and not picked up by our Monocle runner. You can also click into your dependency and see all the generated test cases that are associated with that dependency. So you can see here, we thought it was safe to create all 3 types of experiments. And then you can also see runs associated with them and whether or not they need attention, whether or not they failed when we thought they weren't supposed to fail. We have found a lot of vulnerabilities with Monocle. We found a bunch of misconfigured timeouts. We found retries on the same server, unwrapped RPC calls, Hystrix commands with no fallbacks for non-critical services. And again, users weren't purposefully doing this. They were lacking context in some regard as well. And so ironically enough, after we ran through a few experiments, we were able to detect patterns. between monocles to the point where we could recognize these anti-patterns without having to run a chaos experiment. And it allowed us to run less experiments in production, and it will probably continue doing so over time. So with more automation comes the need for more safety checks in addition to the ones we already had. So one of them is we can explicitly add those curated impacts, such as SPS, stream starts per second, sign-up, login, or downloads. And the runner will not run experiments with known impacts. And so a user can go ahead and add an impact directly through here. They can delete one too. There's an audit log, though, and you can put in a reason for adding or deleting them. So CHAP's monocle, in summary, has given us crucial optics in one place. It's given us automatically generated experiments, automatically prioritized experiments, and it has helped us find vulnerabilities before they become outages. It's also reduced the cognitive burden when exploring unknown unknowns with teams. So one of the biggest things with chaos engineering is how the tools have influenced the culture. I think that's the biggest win for a tool is if it's actually influenced the process and the culture, and that can be really hard to measure. And some of the ways that it's happened at Netflix is we've moved from a culture of what happens if this fails to what happens when this fails. And we've also had higher confidence in the ability to deal with disasters as they happen. There's a greater trust in injecting purposeful failure techniques. And so, not all these things are solely derived from chaos. They are an amalgamation of different resiliency efforts that we have at Netflix. But these are things that we have seen change over time and be successful as a result. So if I can leave you with some key takeaways today, it's that pervasive cultural patterns play out when both implementing and advocating for chaos engineering. Don't ignore them. Teams have explicit trade-offs to make under pressure every day when determining what to work on. As chaos engineers, we focus on exploring these vulnerabilities and providing context to teams about the trade-offs that they're making, and helping teams resolve these vulnerabilities before they become full-blown outages. Safety monitoring and thorough investigations are key when trying to surface system vulnerabilities and trying to show teams why they're important. And if I can leave you one final note, it's that it's not to lose sight of your company's customers or your coworkers. The most important customer is your actual business, so don't lose sight of why you're doing these chaos experiments. When you think of your chaos experiments, you should keep a watchful eye on your most important business metric, like at Netflix not being able to stream a video. So even though chaos engineering isn't just failure injection, it's also understanding why things get into certain states to begin with. And it's not the means to an end for your resilience stories. There are several different things that make systems resilient, but none of that can be done without the humans in the loop. Thank you.